This lesson is a little bit controversial because it is about when Bayesian methods should and should not be used, and that is a very opinion-based type topic. I will also, in this lesson, tie in when Bayesian methods are used, because this is a different but overlapping concept compared to when they should be used. When are they used versus when should they be used? All right. So I'm going to break the topic down into a couple of different questions. The first is, when do researchers use Bayesian methods? This will give a sense for how they're being used currently, at least in the social sciences, which is the area I am in. Next, I'll cover when should researchers be using Bayesian methods, and then also when they should not. It is really important that you take this lesson as being filled with my opinions and not as indisputable facts. Experts in the field can have varying opinions about when to use Bayesian methods and when not to, and that's okay. For example, I know equally impressive and smart statisticians with completely opposing views. One of my friends feels that you should never use Bayesian methods, and a few of my others feel that you should always use them. There are many people that fall in this dichotomous stance, but I'm much more in the middle, and I try to look at this more of a practical issue. So I approach the issue with respect to when Bayesian methods can be useful and when it might be best to use alternative estimation approaches. Not everyone is going to agree, but what you should do, what I recommend, is that you should collect your own evidence and figure out how you feel about it as you gain experience with Bayesian methods. So our first question is, when do researchers use Bayes? This goes back to a large review I was a part of, and I'm going to show you some results that break down the reasons that papers cited for using Bayesian methods. First, we can take a look at who is using Bayesian methods. Here's a graph that is already a bit outdated, but it looks at 25 years of Bayesian papers that were published. And the y-axis in this case is the number of articles. But I will say, if we convert this to the proportion of articles, the trend lines look similar to each other if you plot them against each other. We can see that the blue line is drastically higher than others, and this is fields like engineering and mathematics who are using Bayesian methods for a long time at a much higher rate. Where here I am in the red line, this is the social sciences. In this case, it turns out that Bayesian methods are increasing in prevalence, but they're sort of slowly increasing. They're still vastly outnumbered by traditional frequentist methods in the literature. I think it will continue to rise, but probably it will be a long time, maybe even never, when Bayes overtakes conventional methodology. We'll see. Here we can see of the empirical papers within psychological sciences that used Bayesian methods. We can see why authors cited why they needed to use Bayes, or why they did use Bayes. The most prevalent category that we saw is that they were forced into using Bayesian methods. This could be because of some computational problem that arose, or they're avoiding numerical integration, or because the model that they wanted to estimate maybe could only be done using Bayesian methods. Maybe they're implementing something like the near zero prior, and so they needed it. This is an important finding, I think, because it shows you that the bulk of papers are not using these methods because of philosophical reasons. There are very practical reasons that are driving the use in these larger categories. Many of the lower cited reasons listed here are tied to, at least to some extent, the use of priors and how results can be interpreted. At any rate, I think it's really interesting to see why people are using Bayesian methods. And I have a feeling that we'll see some of this shift as the field grows and we learn more about how Bayes can be useful, especially in fields like structural equation modeling or modeling frameworks like SEM. The next question is, when should researchers use Bayesian methods? So again, this is my opinion, so take it for what it's worth. I'll start by saying I think Bayesian methods are far more interpretable and interesting than traditional ML-based computation because we can interpret the full posterior. I think this is a huge advantage and benefit of using Bayes. However, there are some particular areas where I think Bayesian estimation can have even further benefits. In my view, here are a couple of instances where I would openly advocate for using Bayesian estimation. First off, if you have a specific theory that you want to examine or implement about a parameter, then priors can help you do that. So this is one very substantive-based reason where you would have a theory that you want to include via the prior, and that this is just what you want to test. So one reason where I would strongly advocate for using Bayes is if there was a substantive-based or theory-based reason for doing so. Another reason or category of when I think you should be using Bayesian methods is if you are testing invariance. If you have a model that you're testing some sort of invariance for groups or across time, I see no advantage to using traditional methods. The flexibility that the near zero priors provide is incredibly helpful and can improve fit and overall interpretation. Therefore, I would advocate for Bayesian methods to be used here if possible. The last point I have listed has to do with groups. If you have a relatively small group or cluster, if you're dealing with multi-level models, then Bayesian methods can really help in this situation. Anytime sample sizes are smaller, priors can help increase the information that's provided and you can obtain more accurate results. This is especially the case when you're looking at groups in my experience. Related to this, though, is the more complex issue. So think of known groups or known clusters that this could be very beneficial. But then also think of the latent class situation where you don't know group membership because it's latent. If you suspect, and you're dealing with latent classes, if you suspect a smaller latent class that is smaller relative to the other classes, and you have reasonable priors that you can implement for the latent class proportions, then you will have many benefits in the Bayesian framework. In the case when you have a relatively small class, so it's relative small to the other classes, traditional ML-based or frequentist-based methods have an incredibly hard time finding that small class. Bayesian methods perform so much better, but it is specific to the situation where you have reliable prior knowledge about the approximate size of that class. I'll say more about this on the next slide. So these are the main situations where I think you should use Bayesian methods because there's a clear advantage over conventional methods. Now we can shift and talk about when you should not use them. So I actually thought about this point for a long time before making these slides, and I realized I think that my bias toward Bayesian methods really comes out here. I'm inclined to think that Bayesian methods, if used properly, can be comparable to or outperform traditional methods in most situations. However, there is one case where I strongly advocate against using Bayesian methodology. This is a situation that's tied to something on the previous slide. In the case where you're working with latent classes and you do not know the size of those latent classes or their relative size, and your plan is to rely on default diffuse settings for the class proportion prior, you can really mess things up. So if you have latent classes, let's say here's what can happen. Say you have a latent class situation and you want to test a 3-class model. You have no clue how large the latent classes are relative to one another. So you implement a default diffuse prior on the latent class proportions. This diffuse prior setting that is very common and a default setting in Mplus will actually act as a very informative prior on the class proportions. And what happens is it will force the class proportions to be close to equal in size. The prior works great if your classes are already comparable in size, but it is a highly diverging prior, or like a wrong prior, if you have a class that is smaller in size relative to the others. In the case where you want to work with latent classes and you use default diffuse settings for the class proportion prior, then, and when you have one class that happens to be small, then the results you obtain will be wrong. And you likely won't be able to tell that this is the case if you're looking at empirical data results. This, I think, is the most severe don't use Bayes example that I can think of, because the prior setting that you think is default diffuse, if it turns out that you have a class that is very small, but you don't know that you do, that default prior can act as an informative prior and create equal class sizes because of how the default prior is set up. It is aligned with equal class proportions or equal class sizes. So this is, I think, a big case where you have to think, if I have no clue how big my classes are, I don't know, maybe there's a tiny class. If there happened to be, it would be really hard to properly pull that out without using an informative or weakly informative version of the prior. Relying on the default setting can do bad things. So of course, I would also say that if a person has no clue how to properly conduct Bayesian methods, they should not use them. That goes without saying, but this is the biggest sort of no-no that I think Bayesian methods can actually do a lot of harm, and the researcher may not be able to detect that there was a problem.